Hi. Thank you for the invitation. And so today I'll be talking about tensor methods for feature learning. I think many of you here are aware of our work on tensor methods for unsupervised learning of a wide range of latent variable models. We were able to show many strong guaranteed results in recovering the correct underlying parameters of the model. So here we'll see now a different take on tensors and show how they can be extremely useful for feature learning. Right, so what is the notion of feature learning? So the idea is when we have classification or regression tasks, we'd like to first find useful transformations of the data and then carry out prediction. Right, so for instance, for say face recognition, you'd like to first think of like a bag of features. Maybe it's like eyes, ears, and different parts of the face. If we can extract those features first, we hope to have better classification. And the whole framework of deep learning is based on the paradigm that there are these hierarchical features where simple shapes such as lines give rise to more complicated features, and these are very relevant for useful classification. And in speech recognition domain, spectrograms and other transformations have been extremely useful. So the principle I'd like to explore is how to go about finding these feature transformations in an efficient way, and what can we say in terms of, theoretically, when can we learn such feature transformations? Right, so the idea is if I want to now predict the label y given x, there is some intermediate function, phi of x, that is better for predicting y. So how do we go about learning these feature transformations? We can think of learning them from label samples, meaning this function phi will incorporate both information about the label and the input, or we could do it just using unlabeled samples. So that means we can construct these transforms using only the input x. And in practice, in many of these domains, there are many more unlabeled samples than labeled ones. So it is, sometimes more convenient to find these transformations using unlabeled samples. But of course, the challenge is in what scenarios will that be relevant for this particular classification task is unclear. Right? So these are all the questions we'd like to address on when we can find these feature transforms in a principle and with guarantees. And so what we'd like to think of them is in a model-based framework. So if we think of a particular conditional model of y given x, we'd like to incorporate these transforms as some latent variables. Right? So this is the principled way to think about trying to estimate these feature transforms.
This is a very naive question. So you're trying to find a feature function phi to better predict y.
Yeah.
And if you're given unlabeled samples, how would that provide any information about?
Yeah, so because again, that's the question we'd like. In practice, we also have some distribution information for x, right? So that could be relevant in knowing, you expect certain kinds of x. And so that we'll see in this talk precisely how that will be useful as well. So that's the question, yes, we'd like to address. And empirically, people have seen good performance by using even unlabeled samples for better prediction. So that's what we'd like to address. So you'll see that a little later. Let's hold off. So let's think of two cases for these conditional latent variable models, right? So I will have some distribution of y given x. I'd like to also incorporate these intermediate feature transforms. So the usual way that people have done this in practice is think of a neural network, right? So there are now these intermediate layers of neurons that will finally generate the label rather than directly from the input. So we can posit now a model that the label is generated from a feed-forward neural network. So this will be one of the models we'll be addressing. So another model we can think of is the classic setting is to think of a generalized linear model for the label given the input, but we'd like to expand on this and instead think of a mixture of generalized linear models. So instead of like one generalized linear model generating the label, we'd like to now think of it as a mixture. And again, the question is, when can we learn the parameters of these models in an efficient way, right? So indeed, in general, this is challenging. I mean, even the identifiability question is challenging, right? So if you think of a multi-layer neural network, when can we correctly learn the parameters is, highly non-trivial. And in fact, intuitively, we know that if there are a lot of linear layers, we can just collapse them. So there should be non-linearity to make a neural network identifiable, but also non-linearity makes it much harder to learn. So this is the first question that would be natural to ask: when are these models identifiable? But we'd also like to go beyond and also come up with tractable algorithms. So indeed, like maximum likelihood estimation in these models is NP-hard. And in practice, it's backpropagation or EM. All these local search methods have no consistency guarantees. Right, so the question is, can we come up with alternative methods that have guaranteed solution that can correctly recover the parameters of the model under some very reasonable conditions? And indeed, we also would like to worry about sample complexity because we are thinking of these models in high dimensions. So we'd like to have models that are low sample complexity, ideally some low order polynomial in the input dimension. And so we'll see how tensor methods can lead to like guaranteed learning for this class of conditional latent variable models under some set of conditions. So we'll see what those are. So indeed, I'm sure many of you here are aware of the basic spectral methods. So these are matrix operations which involve finding low-dimensional projections of the data, right? So there's the basic PCA where you'd like to find low-dimensional subspace that captures the data well, or you can think of the CCA setting when there are multiple views of the data. You'd like to find the maximizing canonical correlation directions, and these involve spectral decomposition of matrices. But what we'd like to see is, can we go beyond to tensors? Right, so can we, PCA and CCA only work on like pairwise relationships? Can we think about higher order moments, and can we decompose them efficiently to learn parameters of a wide range of probabilistic models? And indeed, we can think of representing these higher order moments, and that's where the tensor framework comes up. So if we think of a matrix, we can think of the indices of these matrices representing correlation between every pairs of variables. Now, if you think of, say, a third order tensor, similarly, we can think of the tensor incorporating the third order moment for every triplet of variables. So we can represent moments in this form. And now the question is, what can we do with tensors? Right? So we can similarly define spectral decompositions similar to the matrix eigenvalue problem. So if the matrix, we'd like to find the most compact sum of rank 1 terms that fits the matrix. Similarly for the tensor, the notion of a CP decomposition is to find the best decomposition of the tensor into sum of rank 1 terms. And indeed, this is also a non-convex problem, and the question is this guaranteed to converge to the right solution? And and what we had earlier analysis, and there was indeed work even before us that showed that in many cases, indeed, that we can correctly get the solution. So one of the cases is the orthogonal setting. So if these components are orthogonal to one another, then we can correctly recover the decomposition of a tensor. We can get the global convergence in that setting. And indeed, what we saw was not just for orthogonal tensors. Even if the components are non-orthogonal, if they're linearly independent, that suffices to get the correct decomposition. So you see here, going from matrices to tensors, we get more information. Here in the matrix, you can only recognize the components up to an orthogonal representation. But with tensors, we can also recover non-orthogonal representations. And in fact, in our most recent work with Rong A and Majid, my student, what we have shown is we can even recover over complete representations. So for a tensor, we can have identifiability even when the rank is more than the dimension. Right? There are more number of terms than the input dimensionality. And for a matrix, this is impossible. So with tensors, we can now extract much better information than using matrix operations. So tensors are indeed very powerful for learning a range of latent variable models. So the question we'd like to address now is how can we learn conditional models using these tensor methods? Right? So now with conditional model, we have label and we have input. And so we can construct different kinds of moments. We can construct, the usual cross moment between the label and the input, but we can also now construct higher order moments. And now there is no reason to limit to just, these linear versions or multilinear versions of input and the label. Right? So we can also think of having some feature transformations of the input and use that to construct the moments. So the question is, what is the right feature transformation to construct these moments? So that's how we will think of feature learning in the sense that we want to find good transformations of the input that will lead to efficient construction of these moments. And of course, the question is, what will these moments reveal? And if I do spectral decomposition of these moments, what kind of conditional latent variable models can I learn efficiently? So that's what we'd like to address in this talk. So we are now taking, this is a different take on feature learning because we want to think of learning first features in order to construct these cross moments between those feature transformations of the input and the label, and then exploit them for learning these conditional latent variable models. So what we'll see is it's very useful to construct these feature transformations based on the input distribution. So this is why the input distribution also matters. Because here, if you think of these moments between the input and the label, it includes the joint distribution of both the input and the label. So it's not just the conditional distribution of the label given the input that matters, but also this joint distribution. And so we'll see what kinds of these features can be constructed that will be useful for such cross-moment construction. So let's see, let's incorporate now a generative model for the input, and let's, first I'll show you some possible feature constructions, and then I'll justify why they are the right ones to look at. Right, so the popular one that's been used before is the so-called score function, which is the gradient of the log of the density function. So in this example, if there is this one-dimensional density function, you can construct its score, and intuitively that captures local variations of the density function. Perhaps it's more visible in this two-dimensional, the famous Swiss roll example. So this is the density function, and the vector field here now represents the score function. So intuitively, these score functions are representing local variations in the density function, right? So, and these score functions have been used before for, as features in many settings. And the strength of these methods are they work even for non-normalized models. So if you posit restricted Boltzmann machines where partition function is intractable, if you look at this gradient, right, the partition function disappears. So they become tractable for estimating non-normalized models. So that's the context where score functions have been used before. And to estimate this, we only need unlabeled samples. So that's the good thing, because we can now use a lot of unlabeled samples and construct, estimate these score functions efficiently. Right, and also there has been recent work by Alain and Bengio, which shows that you can do quick approximations of these score functions using autoencoders, assuming you go to the optimal reconstruction in the autoencoder. So, so the idea is one option is to incorporate these core functions as the transformations to construct the cross moments. Right, so we can use this score function feature instead of directly the input to find the cross moment between the label and now this score function feature. But what is the drawback? The drawback is if typically we can think of x as a vector, right? So we have vector inputs. The score function is again just a vector. So this way we can only construct like just the first order cross moment between the two, right? So we can only, so if say y is a scalar, as in the simple case of binary classification, then this moment is just a vector. So, but we'd like to now go to tensors. We would like to go to these higher order moments. So is there a hierarchy of such functions that can be used to construct these cross moments? So what we came up with is this notion of looking at now higher order derivatives of the input distribution. So we call them higher order score functions, and now this way we can now have progressively higher dimensional features, right? So now say if x is a vector, now the second order version would be a matrix, the third order score function is a tensor, and so on. So now if we incorporate them into constructing these cross moments, we can now get these whole hierarchy of moments, ranging from matrices to higher order tensors. So this way we now have the flexibility to have moments of any order. So now the question is, why is this the right transformation? Why are these moments the right ones to look at? So we'll look at this cross moment between the label and these core functions. So the result, what we establish is, in fact, what are these moments revealing? So they are nothing but the expected values of the gradient of the label as a function of input. So this g of x is nothing but the conditional expectation of the label given the input. And if we look at these cross moment of the label with respect to the score functions, what we obtain are expected gradients of this function. So this result, there's the classical Stein's lemma, which is for like order 1, and usually it's shown for Gaussian distributions, but it's a straightforward extension to also think about more general distributions. And so for any continuous distribution, we have this result that by looking at these higher order score function, we can get access to expected gradients of the label as a function of the input. So that's why we call this framework as an approach to have a discriminative information, right? Because we are having now access to information about how the label changes as a function of input through these gradient forms. And now we can apply tensor decomposition. So we can look at these cross moments and we can find decomposition of this into rank 1 components. And we can now construct, in practice, so with the model-free approach, what we can do is we can just construct we can essentially project the input along these directions, apply some nonlinearity, and use them as features for classification. So that's the overall framework that we'll construct these core function features, and that requires only unlabeled data. And now once we have labeled data, we can construct cross moments between the label and these core function features. And what we established is that these cross moments capture expected gradients of the label as a function of input. So we can incorporate these moments and find spectral decomposition. And then we can use them to extract discriminative features. Right, so this is the overall framework. Now we'd like to ask how can we use this to provide guarantees for learning those conditional latent variable models. Right, so what kind of guarantees does this method have? So let's revisit the mixture of classifiers model. So here now we posit that the label is generated now as a mixture of different classifiers. So this G is some nonlinear function, and so now H is selecting one of the classifiers. So now what we show is if we can construct the score functions of the input, and now we'll construct these moments between the label and these score functions, we can find a decomposition of such a moment, right? So this is third order moment, so we can find a CP decomposition of this tensor. The rank 1 components directly correspond to the weight vectors. So by finding a tensor decomposition, we can consistently learn the weight vectors in a mixture of classifiers model. So these are the first results to have guarantees for learning nonlinear mixtures, nonlinear regression mixtures. We can learn using the tensor methods. And you see here that even to learn this conditional model of the label given the input, we need input information. We need information about the input distribution. So that is critical to learning these conditional models. So the other result, we are very excited about is learning this multi-layer neural network. So here I'll just show the 2-layer one, the more general cases involved. So in the 2 layers, let's say there is this first layer and there's some nonlinearity, right? So these neurons take these linear projection and then apply some nonlinearity. And then second layer, I'll just assume a simple linear combination for now. So we have now the first layer is nonlinear, the second layer is linear, and we'd like to ask, can we consistently learn the parameters here? Right? I mean, this is a hard problem, right? Because there is now first the nonlinearity and then there's a linear combination. And in fact, this is just a scalar. Right? But what we show is if we have correct estimation of the score function of the input, we can correctly estimate the weights of the first layer. In fact, again, the rank 1 representation of this, the CP representation of this tensor will be exactly the different weight vectors of the first layer. So, and in fact, the identifiability result also states that this model has to be nonlinear here. So this mapping here has to be nonlinear. And the sample complexity also depends on how nonlinear this model is. So we can, correctly, we can kind of transparently have conditions that characterize what kind of, nonlinearity is required for learning these models consistently. So no, I don't have time for details, but the interesting thing is even with now an additional layer, we can still uncover what are the correct weights in this first layer of the neural network. And we just have some preliminary results on, yeah.
So what's the distribution of X that this S3 corresponds to?
So any arbitrary distribution, right? So if we had this, access to that distribution. So we'd like to estimate it, and again, there's a whole methodology to how to correctly estimate these core functions. But here we are assuming, suppose we have the correct estimates for the score functions. So it can be any arbitrary input distribution, and based on that input distribution, we construct these core functions.
And the nonlinearity?
And the nonlinearity, so it has to be any nonlinearity that has like derivatives up to third order, that has a non-zero third order derivative. That's because we are looking at third order moments here. And in fact, we can even make it more transparent for specific nonlinearities. I mean, a popular one is a rectified linear unit or the ReLU, so we give precise conditions on when that model becomes identifiable. And I can discuss more offline about that. And so this now kind of has a nice intuition that nonlinearity is critical for identifiability as well as learning of these multi-layer neural networks. And our framework directly exploits that fact here. And so we only have some preliminary results currently for MNIST data, and we are now scaling this up to many other models, and we're very excited to see some nice results just based on even without much tuning. So the idea was even for score function, we just used the autoencoder framework. So we could have done more sophisticated score matching algorithms, but we just did this simple autoencoder. We trained autoencoders, and then we constructed score function using the Taylor series approximation argument for these reconstructed functions from the autoencoder. And then we can find these cross moments, and then we find tensor decomposition of this, and then we can extract the directions from this tensor decomposition, and then construct these discriminative features that we feed to an SVM. And so what we found was results at the range of like 96% just with one layer of such framework. And so we are now trying multi-layers, and we are also trying much more challenging data sets using this framework. So to conclude, we found these tensor methods to be highly effective for learning conditional latent variable models as well. So the idea is even to estimate the label given the input, it's crucial to incorporate the input distribution. So, and we saw that score function features are relevant forms of or relevant information about the input distribution that's needed for estimating these conditional models. And the idea was to find cross moments between the label and the score function features, and to do tensor decomposition. And given that tensor decompositions are very fast and scalable, we can apply them to large-scale data sets, as well as in theory, we get all these nice consistency guarantees using those methods. And as a general framework, we have a number of other non-convex methods that we are looking at. And the question is, we are kind of building more and more class of problems where we can establish guarantees about non-convex methods. So I encourage more people to think about non-convex methods as not just going to a local optimum, but when we can obtain guaranteed solutions. And this piece of work is in collaboration with my excellent students, Majid, Hani, and Niranjan, and the papers are available on my website for more details. Thank you.
Okay, we have time for one quick question while the next speaker sets up.
Does this method depend on successful learning and ongoing knowledge?
Right. So, theoretically, this assumes that you have the right score functions, right? You have the right estimate of the score functions. And the question when we can learn this is a whole other question. And there are there's a body of work on that. So in this work, what we're assuming is if we can get the input distribution right, we can also learn these conditional models efficiently. So that's the message of this work.
And if we got a recurrent neural network, would this kind of method be?
Yeah, so we are looking at that as well. I believe we can give guarantees. So so this is something we're working on currently. Yeah.